Hello, and thank you for joining me. In this presentation, I will explain the analytical structure of PPACT Studio and the current scope of its verification from an engineering perspective. PPACT stands for Performance, Power, Area, Cost, and Traffic. PPACT Studio is an architecture exploration framework for comparing AI system design alternatives before physical implementation and for analyzing system-level bottlenecks and trade-offs. The important point is that PPACT does not calculate a single performance number in isolation. It analyzes how multiple elements interact within one system, including the host processor, AI accelerator, memory subsystem, pre-processing architecture, process node, and computational precision. PPACT also goes beyond presenting the final results. It provides traceability into why those results occurred and recommends which architectural changes may be worth comparing next. Throughout this presentation, I will use Study 001 as a consistent example. We will examine what PPACT Studio calculates, how its results should be interpreted, what has been verified, and equally important, what has not yet been validated. This page shows the overall analytical flow of PPACT Studio. The process begins with a system architecture defined by the user. The inputs include the host CPU, AI accelerator, memory subsystem, ISP, workload, process node, precision, and design constraints. These inputs are passed to the analytical model. The model calculates compute time, memory service time, host overhead, bandwidth demand and supply, and the overlap between computation and data movement. The results are then reorganized into a system flow view. For each station, the model calculates processing time and utilization, evaluates link load, and identifies the current limiting element in the system. Finally, it derives system-level metrics such as latency, pipeline capacity, delivered throughput, power, area, cost, and traffic balance. The important point is that all of these results follow one consistent analytical path. The model does not fit arbitrary values or perform stochastic sampling on each run. Model coefficients are obtained from the managed component library. For this reason, the PPACT Studio user interface is not simply a screen that displays numbers. The analytical model comes first, and the user interface presents the results produced by that model. Let us now look more closely at what the analytical model actually computes. First, the processing time of each station is calculated independently. For example, the model calculates host service time, memory service time, and accelerator service time. Each station time includes computation and data transfer components. Where those activities can occur concurrently, the overlapping portion is accounted for as overlap. The model then calculates the execution latency of the complete path. Pipeline interval, however, is determined by the largest stage time. In other words, the slowest station limits the sustainable processing rate of the system. This distinction is why PPACT Studio does not represent performance with a single number. Single job rate is the inverse of total latency. It indicates how quickly one job can be completed. Pipeline capacity is the inverse of the pipeline interval. It represents how many jobs the system can sustain in steady-state operation. Delivered throughput is the smaller of pipeline capacity and the actual application target. For example, even if a system has the capacity to process 118.01 jobs per second, if the application requires only 60 jobs per second, delivered throughput is reported as 60 jobs per second. Keeping these three performance concepts separate is essential for understanding Study 001. All other system conditions remain unchanged. The starting point uses LPDDR5, and the candidate uses HBM3E. It is natural to expect that a major improvement in memory performance will make the entire AI system proportionally faster. But system performance is not determined by the peak capability of a single component. The chart shows the station times for the two designs. At the starting point, the host takes 8.474 milliseconds, shared memory takes 2.121 milliseconds, and the accelerator takes 2.519 milliseconds. With faster memory, the host time falls to 7.270 milliseconds, shared memory time falls to 0.084 milliseconds, and accelerator time remains unchanged at 2.519 milliseconds. Because the longest station determines the pipeline interval, the interval changes from 8.474 milliseconds to 7.270 milliseconds. As a result, execution latency decreases from 11.523 milliseconds to 9.810 milliseconds, while pipeline capacity increases from 118.01 inferences per second to 137.54 inferences per second. So, there is a clear improvement. However, delivered throughput remains unchanged at 60 inferences per second. That is because the application target itself is 60 inferences per second. And there is one especially important observation. The host remains the limiting element both before and after the memory change. The faster memory therefore produces a real improvement, but the full performance gain of the memory subsystem does not translate directly into an equivalent system-level performance gain. There is also an important detail about the station times. The station times should not simply be added together and interpreted as execution latency. The three station times sum to 13.114 milliseconds, while execution latency is 11.523 milliseconds. These values represent different decompositions of the system and share some underlying calculation terms, so they do not have a simple additive relationship. On the next page, we will examine this interaction more closely through the host station. This is the first system-level observation from Study 001. This page addresses a natural question. If only the memory was changed, why did the host station time change as well? The key is that host station time does not represent pure CPU compute time alone. Host station time consists of host computation time plus the host's own DRAM transfer time minus the portion in which those two activities overlap. On the screen, this is expressed as station time equals compute time plus transfer time minus overlap time. Let us break down the values using that definition. The host station time shown on screen is 8.474 milliseconds. Adding the two displayed values gives 8.473 because the total is rounded once rather than being added from two already rounded parts. After changing the memory to HBM3E, host compute time remains unchanged at 7.239 milliseconds. Data weight, however, falls sharply to 0.031 milliseconds. The resulting total is 7.270 milliseconds. So the CPU itself did not become computationally faster because the memory changed. The host station became faster because the CPU spent less time waiting for data. The same decomposition also explains why the accelerator station does not change. Its 2.519 milliseconds is dominated by computation, with very little waiting time. As a result, changing the memory leaves that value essentially unchanged. This example illustrates why components in PPACT Studio should not be interpreted as completely independent numbers. At the system level, changing one component can affect the service time of another station. This page explains why PPACT Studio does not reduce performance to a single metric. Execution latency is the time required for one job to travel through the complete system path. In Study 001, the starting point execution latency is 11.523 milliseconds. Single job rate is the inverse of that latency. It expresses the same single job behavior as a rate, which is 86.78 jobs per second. It should not be interpreted as an independent measure of concurrent processing capability. Pipeline capacity is the inverse of the pipeline interval determined by the slowest station. It therefore represents how many jobs the system can sustain under a continuous workload. In Study 001, the starting point pipeline capacity is 118.01 inferences per second. Delivered throughput applies the actual application target to that capacity. In this study, it is 60.00 inferences per second. With faster memory, both execution latency and pipeline capacity improve. Delivered throughput, however, remains unchanged. The system was already able to satisfy the application target of 60 inferences per second. This is why saying only that performance improved by a certain percentage can hide important system information. Whether one job finishes sooner, whether sustainable processing capacity increases, and whether the application actually receives more results are three different engineering questions. PPACT Studio does not collapse those questions into one performance score. The right-hand column on the screen shows where each value appears in the actual interface. Execution latency and delivered throughput appear as rows in the measured results table. Pipeline capacity is the metric used by the performance axis of architecture balance. Single job rate does not appear directly on the screen. It is included here only as a reference value to explain the definition. One point should be especially clear. The user sees one spider chart on screen, and that chart is architecture balance. Its performance axis uses pipeline capacity and only pipeline capacity. For study 001, 137.54 divided by 118.01 is approximately 1.17 times. The two boxes at the bottom summarize this distinction. The left box states that there is one spider chart on screen and that its performance axis reads pipeline capacity. The right box explains why the four performance quantities remain distinct. Because delivered throughput is capped by the application target, it cannot show the 16.5% increase in available pipeline capacity. That is why the performance axis of the spider chart uses pipeline capacity, even though pipeline capacity is not printed as a row in the measured results table. Now let us consider how PPACT Studio manages reproducibility. The upper part of the page shows the analytical path from configuration to recommendation. Below it are three properties of that path. The first is determinism. The same configuration produces the same result. Because the model does not use sampling or random seeds, repeated executions do not produce different outputs. The figure at the bottom illustrates this. When the same configuration is executed 3 times, all 3 points fall at exactly the same location, and pipeline capacity is calculated as 118.01 inferences per second every time. The comparison on the right illustrates how a sampling-based model could produce different values across repeated runs. The second property is traceability. Each recommendation is linked to the rule identifier that generated it. The user, therefore, does not need to accept a recommendation simply because the system produced it. The user can trace which rule and which analytical result led to that recommendation. The third property is the freeze against a numerical baseline. In the current release, 6,218 freeze checks compare release outputs against recorded numerical baselines. If a meaningful numerical value or semantic behavior changes, that change can therefore be detected, and the reason for the change must be managed. In PPACT Studio, reproducibility is not simply a claim. It is a property managed through the model structure and the verification process. This page is particularly important for understanding PPACT Studio because not all input values have the same level of evidence. PPACT Studio classifies parameter provenance into 4 levels. The first is published. This category includes values that can be obtained directly from public sources, such as core count, clock frequency, memory interface width, package die count, and precision. The second is derived. These are values calculated from published information, such as peak bandwidth, die area at a target process node, and workload MAC count. The third is estimated. This category includes values such as die area at a reference node, component unit cost, active and idle power, and cycles per work element. The fourth is assumed. These are modeling parameters such as the host memory overlap fraction, bandwidth efficiency, cache area derating, and node scaling factor. The important point is that PPACT Studio does not treat all 4 categories as equally established facts. At present, these coefficients have not been calibrated against measured silicon. PPACT Studio, therefore, does not hide these values or present them as already validated measurements. The current approach is to identify their provenance, version them with each release, and allow users to inspect and challenge the assumptions. A recommendation in PPACT Studio is different from what is commonly understood as an AI prediction. PPACT Studio does not predict in advance that an architecture change that has not yet been evaluated will improve the system by a specific percentage. Instead, it uses the current analytical results to suggest structurally meaningful changes that may be worth comparing next. Let us look at the list actually produced by the engine for study 001. 2 items are classified as direct. The first is to compare an alternative host processor. The reason is that the host is the current limiting element. The associated rule identifiers are host limit 001 and ISP limit 002. The second is to move pre-processing away from the host, because this is expected to reduce host activity. The associated rule identifiers are host limit 002 and ISP limit 001. Two items are classified as contrast. One is to compare an alternative accelerator associated with accel limit 001. The other is to change the memory package count associated with mem limit 002. In both cases, the interface also states that these changes do not directly address the current limiting element. The memory technology change is marked as completed. Its rule identifier is mem limit 001 because that is the change already performed in this comparison. Contrast does not mean that a comparison is meaningless. It is included so that the user can directly examine what does, or does not, move at the system level when a change does not target the current limiting element. Once a recommendation is generated, that architectural change can be entered back into the same analytical model. The magnitude of the actual improvement is then determined from the newly calculated result. The PPACT Studio approach can therefore be summarized in 2 steps. A recommendation proposes the next engineering question worth examining. Re-evaluation provides evidence for that question. Because each recommendation also includes the rule identifier that generated it, the reasoning path remains traceable. This page summarizes every value calculated for study 001 and shows where each value appears on screen. The 2 columns on the left show the starting point and candidate values. The column on the right identifies where each metric is displayed. Execution latency decreases from 11.523 to 9.810 milliseconds and appears in the measured results table. Delivered throughput remains at 60.00 inferences per second and also appears in the measured results table. System power increases from 3.505 watts to 13.195 watts. It appears both in the measured results table and on the power axis of architecture balance. Energy per job increases from 40.39 to 129.4 millijoules and appears only in the measured results table. SoC silicon remains unchanged at 12.02 square millimeters. It appears both in the measured results table and on the area axis of architecture balance. Memory silicon increases from 240 to 1,760 square millimeters, while total silicon increases from 252 to 1,772 square millimeters. Both appear only in the measured results table. System cost increases from $18.82 to $225.11. It appears both in the measured results table and on the cost axis of architecture balance. Thermal power density also appears in the measured results table. Now we come to an important distinction. Pipeline capacity increases from 118.01 to 137.54 inferences per second, but it does not appear as a row in the measured results table. It appears on the performance axis of architecture balance and in the engineering conclusion text. Traffic balance increases from 29.73% to 34.65% and appears only on the traffic axis of architecture balance. Single job rate does not appear directly anywhere in the interface. Therefore, if you look only at the measured results table and try to find the source of the 1.17 times value in the spider chart, you will not find it there. That ratio comes from pipeline capacity, which is not printed as a table row. Architecture balance is the only spider chart shown on screen. Its 5 axes use pipeline capacity, system power, SoC silicon system cost, and traffic balance. The starting point is normalized to 1.00 times, and the candidate shows the relative change on each axis. This is not a composite score. It is a normalized view for comparing multiple system-level trade-offs on one screen. The traffic axis should also not be interpreted as an independent design quality score. I will explain that metric on the next page. This page reproduces the measured results panel from PPACT Studio, including the notation and numerical precision produced by the engine. The right-hand column shows requirements and margins. A maximum value represents an upper bound, and a minimum value represents a lower bound. Margin is calculated relative to the requirement, not relative to another design. Execution latency is marked comfortable, with a 51% margin against an upper limit of 20 milliseconds. Delivered throughput, by contrast, is marked critical, with a 0% margin against a lower limit of 60 inferences per second. It meets the requirement exactly, but there is no remaining headroom. System cost retains an 85% margin against an upper limit of $1,500. Silicon retains a 98% margin against an upper limit of 500 square millimeters. No requirement is stated for energy per job, memory silicon, or total silicon. Now let us look at the changes between the two designs. Execution latency decreases by approximately 14.9%. Delivered throughput, however, remains unchanged at 60 inferences per second because the target throughput itself is 60 inferences per second. System power increases by approximately 276.4%. Energy per job increases by approximately 220.5%. Silicon does not change, but memory silicon increases from 240 to 1,760 square millimeters. As a result, total silicon increases from 252 to 1,772 square millimeters. System cost rises from $18.82 to approximately $225.11. So the faster memory improves latency and pipeline capacity. But that improvement comes with substantial increases in power, memory silicon, total silicon, and cost. This is an important perspective in PPACT analysis. The question is not only whether something improved. We also examine what the system had to pay for that improvement. This page clarifies what the term traffic means in PPACT. Traffic does not simply mean the amount of memory bandwidth. It also does not directly represent link utilization or no-see traffic volume. In the current PPACT model, the traffic axis uses a metric called traffic balance. Traffic balance is calculated from the processing rate relationship between the slowest station and the second slowest station. At the starting point of study 001, the host station rate is approximately 118.0 jobs per second, while the accelerator rate is approximately 397.0 jobs per second. The resulting traffic balance is 29.73%. In the faster memory configuration, the host rate improves to approximately 137.5 jobs per second, while the accelerator remains at approximately 397.0 jobs per second. Traffic balance therefore becomes 34.65%. There is an important caution, however. A higher traffic balance is not automatically a higher design quality score. This metric is diagnostic. It indicates how closely the processing rates of the principal stations in the limiting region are matched. Two stations can both be slow and still produce a high traffic balance if their rates are similar. The three pipelines at the bottom of the page are drawn to the same scale. The two on the left are the Study 001 designs with traffic balance values of approximately 29.7% and 34.7%. The pipeline on the right has a traffic balance of 92.3%. Based on that number alone, it may appear much better. But the bars show that the right-hand pipeline is actually the slowest. Both stations are slow, so their ratio simply happens to be close to 100%. Traffic balance should therefore not be used as an independent measure of design quality. It must be interpreted together with other system metrics, including latency and pipeline capacity. This page defines the current level of confidence in PPACT Studio. The first step is to distinguish clearly between verification and validation. Verification asks a specific question. Did we implement the model we defined correctly in code? PPACT Studio currently includes model tests, regression and freeze checks, interface path checks, mutation tests, and independent arithmetic checks. In particular, the mutation test evaluated 162 mutations, with 0 surviving mutations. The purpose of this test is to determine whether the verification framework can actually detect deliberately introduced changes. The independent arithmetic check verifies key numerical results through a separate calculation path that does not use the PPACT engine itself. Validation asks a different question. Does this model represent a real system accurately enough for its intended use? Answering that question requires external evidence, such as measured hardware calibration, external datasets, independent review, and evidence supporting equivalence to commercial products. That external validation has not yet been established. PPACT Studio therefore has substantial internal verification evidence, but that should not be described as validation against real silicon. A central part of the PPACT Studio verification philosophy is to state clearly what has been verified and what has not yet been validated. It is not intended to perform cycle-accurate RTL simulation, signal-level verification, physical implementation, sign-off timing analysis, or measured silicon characterization. PPACT Studio is therefore not designed to replace detailed simulators, RTL tools, or EDA tools. It operates at an earlier stage of the architecture process. Its role is to compare many architecture candidates, analyze their system-level differences, and help narrow the design space to the candidates that justify more detailed investigation. The current engine does not model request queues, arbitration, or contention between stages at a level of detail beyond the interval model. For that reason, terms such as stall or back pressure are not used when they would imply dynamic behavior beyond what the model actually represents. The objective is not to hide the boundary of the model. The objective is to define clearly what should be analyzed in PPACT Studio and when the engineering process should move to a more detailed tool. This page provides the configuration required for another user to reproduce Study 001. The application is Industrial Vision at the edge. The host processor is a 4-core Cortex-A78, and the AI accelerator is an NPU 32x32. The starting point memory is LPDDR5, and the candidate memory is HBM3E, 24 GB. Both configurations use two memory packages. Pre-processing is CPU only. The process node uses the application default, which for the Industrial Vision Edge application resolves to 16 nanometers for the SoC and 12 nanometers for the accelerator. The target throughput is 60 inferences per second. The expected key results are also provided. Execution latency decreases from 11.523 milliseconds to 9.810 milliseconds. Pipeline capacity increases from 118.01 to 137.54 inferences per second. Delivered throughput remains unchanged at 60 inferences per second. The host remains the limiting element both before and after the memory change. The user therefore does not need to accept the conclusion on the slide without checking it. The same configuration can be run directly to determine whether the same evidence is reproduced. This page shows what has been completed and what remains to be done. The current foundation includes a deterministic engine, regression coverage, independent arithmetic checks, and the study library. The next steps include measured coefficient calibration, external blind review, broader corner case coverage, and a reproducibility package. The long-term objective is to build a validated architecture exploration framework. The important point is not to confuse the current state with that final objective. A substantial internal verification framework is already in place. Measured hardware calibration and independent review, however, have not yet been established. At this stage, there is therefore not yet sufficient evidence to claim that PPACT Studio accurately predicts real hardware. The reason this gap is stated explicitly in the roadmap is straightforward. The accuracy of an analytical model against real systems ultimately has to be established through measurement and external evidence. That is the validation work that remains to be done. Finally, I would like to explain how we invite you to review PPACT Studio. We are not asking you to accept the results at face value. If there is an architectural assumption that you believe PPACT models incorrectly, choose one. Then run the corresponding comparison in the public preview. Inspect the raw metrics and examine how the limiting element is determined. If a recommendation is generated, trace the rule that produced it. After reviewing that evidence, if you still disagree with the model, we welcome that challenge. If the disagreement remains after the trace has been examined, it can become more than a difference of opinion. It can provide engineering evidence for a future validation study. We welcome technical feedback, counterexamples, and alternative modeling assumptions. The review philosophy of PPACT Studio is simple. Do not accept the results simply because the tool produced it. Reproduce it, inspect the assumptions, and examine technically where the available evidence may not be sufficient. Through that process of review and feedback, we intend to continue strengthening both the PPACT Studio model and its verification framework. Thank you for your time.